Assalamualaikum warahmatullahi wabarakatuh. We are from Group 12. My name is Nur Afika binti Hashim. We are going to discuss about Experiment 11. There are two objectives in Experiment 11. One is to determine the output coefficient of Venturi meter, and two, to investigate the validity of Bernoulli theorem. For introduction, Venturi meter. The Venturi meter can be used to understand how fluid flows through a constricted system. In constricted system, pressure change can be used to calculate the change in flow rate. Venturi meters are frequently used in wastewater collection systems, water treatment plants, oil pipelines, and combustion engines. Measuring flow rate is incredibly important in systems where a precise mixture is required. Theory. In this experiment, we are using Bernoulli equations, which is shown in the red box. According to the Bernoulli theorem, every section in the flow of a liquid, the total of the static head and the kinetic head are constant. By using continuity equations, which are shown in the blue box and the purple box, we can obtain the actual rate flow, which is shown in the green box.
Thank you, Afika. Now let's move on to the experimental setup and our results. My name is Fahmi and I will guide you through this section. So, for the materials that are used in this experiment, we use the Venturi meter, which is on the left there, and also a stopwatch and also a hydraulic bench. So, to start the experiment, we need the pump is started and the water will start flowing into the Venturi meter, and then we need to release the air bubble inside the tube. After that, the flow rate was changed until the reading on the manometer showed 280 millimeter. 280 millimeter is our H1. So the time taken to collect 5 liters of water was then measured and recorded. Steps 2 and steps 3 was then repeated by decreasing the manometer reading by 10 millimeters each time until the final reading of H1 is 190 millimeters. So now for our results and discussion. These are the calculations that were used to calculate multiple values. First of all, we have the difference, which is the value of H1 minus the H2, and then we have the actual flow rate, the area pi d squared over 4, the ratio d2 over d1, the theoretical flow rate, the discharge coefficient, the velocity, and also the total head. Note that this is the calculation for the first results only, which is the 280 millimeter as the H1. So we need to repeat this a couple times to get the results for different value of H1. This is the table 1, which is the complete version of the calculated one from our H1 and H2 reading. And then we have table 2, which is also the simplified version and also the calculated version from our previous calculations. So our results is presented in table 1 and table 2. We observe a linear relationship between the difference of manometer readings, which is H1 minus H2, and the flow rate. So additionally, the discharge coefficient showed a linear increase with the flow rate as seen in figure 1, which is this one. So you can see that the discharge coefficient and flow rate is linear, and also the square root H and flow rate is also linear. So the Venturi effect is the reduction in fluid pressure that results when fluid flows through a constricted section of pipe. So according to Bernoulli's theorem, the velocity of fluid will increase when the pressure of fluid decreases, or vice versa. So the pressure in wider tube is higher than pressure in narrower tube. So meanwhile the fluid speed in wider tube is lower than narrower tube. Therefore the reading of H1 is always higher than H2 in this experiment. By adjusting the flow rate, we found that the value of H1 and H2 will change accordingly. From the graph of square root of H1 and minus H2 versus flow rate, we can see that the square root of H1 minus H2 increases linearly with Q as seen here. From the graph of the discharge coefficient versus Q, we can see that the discharge coefficient increases linearly with QA as well. So overall, this experiment highlights the importance of understanding the principles of fluid dynamics and Venturi effect. By studying the relationship between flow rate, pressure differential, and discharge coefficient, we can better design and optimize fluid systems for various applications. So for our applications, I will pass this to Lim Wei Liang. Thank you.
Thank you, Fahmi. I'm Lim Wei Liang, and I will now discuss the implications of our experiment and its real-world applications. The Venturi effect and Bernoulli's theorem have practical applications in various industries. One notable example is air intake systems in engines. Flow forms inspired by the Venturi effect are used to optimize the airflow, enhancing combustion efficiency and overall engine's performance. Researchers such as Shu Qingguo and others have conducted experiments to study the flow of air in the intake manifold pipe. They found that under certain conditions, the flow is smooth and ordered, known as laminar flow. However, as the Reynolds number exceeds a critical value, the flow becomes turbulent and causes variations in velocity over time. These variations result in pulsating pressure that can increase the load on the airflow and affect engine performance. To ensure efficient airflow, the design of the intake manifold must consider and control these pressure fluctuations. The Bernoulli equation plays a crucial role in determining the pressure and velocity distribution along the pipe. It helps us understand the dynamic efficiency of the airflow and guides modifications to the pipe geometry. Additionally, the Reynolds number, which depends on the diameter and length of the pipe, helps us investigate the type of airflow present, whether laminar or turbulent. Understanding fluid dynamics and the principles we studied in this experiment can also contribute to advancements in aerospace, automotive, and manufacturing industries. By optimizing fluid systems based on the relationship between flow rate, pressure differential, and discharge coefficient, we can design more efficient and effective systems. In conclusion, our experiment provided valuable insights into the Venturi meter, flow form, and Reynolds number. The findings support the principles of the Venturi effect and Bernoulli's theorem, highlighting the importance of fluid dynamics in various applications. By further exploring these principles and conducting additional research, we can continue to innovate and improve processes in industries where fluid flow is crucial. That's all from us. Hope you enjoyed this video. Thank you.